Okay, so I'm reliably informed that there's not much in the way of further maths on TikTok from somebody who uses TikTok a good deal, I think. I'm going to go on a mission to set things right. I'm going to start off with some simultaneous first order differential equations, sometimes called coupled first order differential equations. So there they are. I'm going to solve them. I'm going to eliminate y to obtain a second order differential equation for x in terms of t, and find the general solution, and then find the corresponding general solution for y. I've got a couple of initial conditions there to find the particular solution. So here we go. So here are my two equations. I'm going to call them 1 and 2. And what I'm going to do, I'm going to use equation 1 to get y and dy by dt and stick it into equation 2. So I'm going to get that and 4y and substitute to eliminate the y. Now rearranging 1 gives me 2y equals, that's all right. I'll need 4y, but 2y will do. To get the dy over dt, I'm going to differentiate equation 1. So differentiate dx over dt gives me d2x over dt squared, the second derivative. And that's going to be equal to minus dx over dt. Remember, I'm differentiating in terms of t here, so it's not. So you've got to be careful. And then 2 dy over dt. And then I'm going to pop those into the equation 2, because rearranging my differentiated equation, I'll get 2 dy over dt equals. And if I double 2, rather than have some fractions in there, I can have 2 dy over dt, which I know in terms of x and t is minus 2x minus 8y and 2 e to the minus 2t. So this tells me what the 2 dy over dt is. I'll replace it with that. Minus 2x, and then I've got minus 8y. I've got 2y here in terms of x and t's, so I can replace it with that. And then I've got a 2e to the minus 2t at the end. So I've eliminated the y now. I've got a second order differential equation with x in terms of t. Tidying up a bit, put it all on the left hand side apart from the bit with just the t's. So d2x over dt squared. And then I need the dx over dt term. Well, I've got 1 on the left and minus 4 on the right. There's going to be 5 of them on the left. And the x's, well, I've got minus 2x and a minus 4x on the right. So I'll have plus 6x on the left. And that's all going to be equal to 2 e to the minus 2t. And that's my second order differential equation. Here's my auxiliary equation, standard procedure. And solve it, give me m is equal to minus 2 minus 3, which gives me my complementary function for x in terms of t is a e to the minus 2t plus b e to the minus 3t. I also need the particular integral for 2 e to the minus 2t. Now normally it would be something times e to the minus 2t, but that's actually part of the complementary function. So I stick anything times e to the minus 2t, I'm going to get 0. So I need to put an extra t in there. So I need to stick x, dx over dt, and d2x over dt squared into the second order differential equation to find out what the k is. Dx over dt, I need to use the product rule here. Differentiating the t gives me k e to the minus 2t, and differentiating the minus 2t gives me that. I can tidy up a little bit, take a factor of k e to the minus 2t out. Differentiating again to give me d2x over dt squared. Again, the product rule, differentiate the e to the minus 2t, just put a minus 2 in front and differentiate that bracket. Again, making the minus 2. And I can simplify this a bit as well by taking a 2k e to the minus 2t out. And I get that, and that all simplifies down to 4k e to the minus 2t, t minus 1. So I'm going to put both of those, the dx over dt and the d2x over dt squared, into my original second order differential equation. So there's the d2x over dt squared. Then I want 5 dx over dt's, and I want 6 lots of x, and that's all going to be equal to 2 e to the minus 2t. That left hand side, I'm going to take a k e to the minus 2t out. Could even get rid of the minus 2t's actually straight away. But if I take it out as a factor, I've got 4 lots of t minus 1 and 5, 1 minus 2t's, and I'll have 6t. Like I say, I can get rid of the minus 2t's, not bothered by those, they're never 0. But and also in that bracket, all the t's cancel, which is what I want. And then so I've got k times 1 is 2. So k is equal to 2. So my general solution now with the k in, a to the minus 2t, b e to the minus 3t plus 2t, e to the minus 2t, and you might want to write it like that. So, so there's the x general solution. To get the y general solution, I want to use my rearranged equation, which had y in terms of dx over dt and x. The dx over dt, I have to differentiate my x general solution. Again, factor theory, product rule, differentiate the e to the minus 2t first, and then differentiate that bracket, which is just 2, and then I'll differentiate the b to the minus 3t, which is that. I can I'll take the factor e to the minus 2 e to the minus 2t out. It looks like that. Subbing the x and the dx over dt into 2y equals all of that plus the x. Oh, my word. And then it simplifies down to this. So y is equal to a half of it, and that's my general solution for y. And finally, the particular solution, the initial conditions where x was 5 and y is equal to 0 and t is 0. Something the x1, 5 equals e to the 0, a plus 0, b e to the 0, give me a plus b is equal to 5. And subbing it into the y1, where y is 0 and x is 0, looks like that. And I doubled it, and I got a plus 2b is equal to 2. And solving them, I get a is 8, b is minus 3. And I can pop those, the a and the b, into the original general solutions. A is equal to 8 in the x, and b is equal to 3, and the same with the y's. And those are my particular solutions for the first order differential equation.